Thank you everyone so much for waiting. And I'm Becca, and I am thrilled to introduce our keynote speaker for today, Dr. Amy Mainzer. So Dr. Amy Mainzer is a professor of planetary science at the University of Arizona. Before that, she was a senior research scientist at NASA's Jet Propulsion Laboratory. Her research interests include asteroids and comets, particularly those that approach the Earth, instrumentation for remote sensing, and applications of remote sensing for monitoring invasive species on Earth. Professor Mainzer is the principal investigator of NASA's Near-Earth Object Wide Field Infrared Survey Explorer, or NEOWISE mission, an Earth-orbiting space telescope that is searching for Earth-approaching asteroids and comets. She is also the lead of NASA's Near-Earth Object NEO Surveyor mission, which will carry out a comprehensive survey of asteroids and comets using a dedicated space telescope. The NEO Surveyor mission has entered its preliminary design phase and is scheduled for launch in March of 2026. Prior to joining the Jet Propulsion Laboratory in 2003, she designed and built the Fine Guidance Sensor for NASA's Spitzer Space Telescope as an engineer at Lockheed Martin. The sensor she built was used daily by the observatory to initialize its pointing system throughout its mission from 2003 until its end in 2019. Professor Mainzer serves as the science curriculum consultant, on-camera host, and executive producer of the PBS Kids series Ready, Jet, Go, a TV show aimed at teaching physical science and earth science to kids ages 3 to 8. And she served as a science consultant for the Netflix movie Don't Look Up. Professor Mainzer is the past chair of the American Astronomical Society's Division for Planetary Sciences, the world's largest professional society of planetary scientists. She serves as the chair of NASA's Planetary Science Advisory Committee and is a member of the NASA Advisory Council Science Committee. So without further ado, take it away, Dr. Mainzer.
Hey, thanks so much. I really appreciate the opportunity to talk with everybody here today. I thought what I would do is kind of present a broad overview of why asteroids and comets are important to the study of the origin of life, or just, what are some of the connections between these two topics. And I think, why it's so important for people who study asteroids and comets, similarly, to work with folks who study the origins of life, because we have a lot in common, and there's a lot of mutual connections between these topics. And of course, with any time you have cross-disciplinary work like this, I think it really improves on both fields. So let's go ahead and jump right in. And I think Becca, you'll feel free to stop me if we've got questions or anything like that. It would be really great to get them, and I'm happy to answer questions anytime. I've got a lot of slides here, but I kind of wanted to do this as sort of a broad overview, not just of the stuff I'm personally working on with my group, but also just some of the things that are really fascinating to me in the field that I hope you'll like too. So one of the things about the solar system, it's just an incredibly busy place. I hope everybody can see this, but the green dots here, these are the main belt asteroids. So this is where the bulk of the asteroids in the inner solar system are, between Mars and Jupiter. And we know close to 1 million of these objects now, as of today. Most of these objects stay in very stable orbits. They just keep going around and around around the sun for billions of years. They don't really change their orbits terribly much for most of them, but sometimes there are exceptions to this. You'll notice there's a couple of other interesting structures here. There's a sort of a blob of these blue objects over here and another one over here. It's a little hard to see on the screen, but that is the planet Jupiter. So these are asteroids that are gravitationally bound to Jupiter, and their orbits are sculpted by Jupiter's powerful gravity. You can also see a population of reddish objects in the interior orbits here. These are what we call near-Earth objects, and we know of about close to 30,000 of those, but we believe that this is only the tip of the iceberg in terms of the total population of such objects, and these are the ones we pay attention to from the perspective of looking for potential impactors on the Earth. So what I'm going to talk about today is just sort of how do these things move around through the solar system, what are their characteristics, and how can they have an influence on the origin of life? So let's get started with that. So first, if you want to make asteroids and comets, you first have to make a solar system. And to do that, you basically have a huge cloud of gas and dust that collapses under the influence of gravity. and then is acted upon by gas pressure and rotation, the effects of angular momentum. So what you have is, I just really love this this particular simulation because it really lets you see very clearly just exactly how quickly things progress. This is time in years up here. And so you can see very quickly we start to form condensations out of the presolar nebula and the beginnings of stars starting to kick off here. And then once the process of star formation gets going, it proceeds very rapidly with lots of things being spat out, a lot of objects of different masses, and each one of these is a solar system, presumably. So if we zoom in now on what's happening with each of these little individual objects that are being born out of this presolar nebula, now we can really get a sense for how we get solar systems. So if we just, I'm going to kind of step us forward here on this movie. But basically now we're zooming in on each one of those little stars that formed out of the cloud there, and you can start to see a disk of material forming around each one, and it's again being acted upon by the joint influences of gravity and angular momentum and gas pressure. But basically, you very quickly start to condense instabilities in the disk, and you have local regions where the gravity is a bit stronger, the material starts to accumulate, and not only do you get stars, but you very quickly start to produce the seeds of planets, as well as some of the planetesimals that don't quite make it into to full planetary mass objects. So basically, moving right along here, you can quickly see we get all kinds of varieties of different solar system disks forming out of the material, leading to all kinds of different planetary systems. Now, in our case, we have an asteroid belt and a bunch of small bodies that are leftovers that didn't quite get swept up into planets. And that's, in a nutshell, how you get asteroids. Most of the material goes into planets in the central star or stars in the solar system, but a lot of it gets left behind, and that which does not get swept up eventually goes into what we know today as asteroids and comets. So you can see the disks really starting to form here. You can see gaps as planets are accreted and start to clear out material, but not everything makes it into a planet, is the upshot of this. So I just absolutely love this photo here. This is recent data taken with the Atacama Large Millimeter and Submillimeter Array, or ALMA. These are pictures of real solar systems. So previous slide we had the simulations, and here we have the actual data. So these are actual solar systems in the process of forming their own planets and their own asteroid belts. And you can see here the gaps being cleared out as the planets sweep up material, but there's a lot of stuff left over. So presumably each of these solar systems have their own asteroid belts and swarms of comets and so forth. So if we zoom in on one of these in particular here, you can get a sense of the scale. This is an object here called HL Tau, and these are millimeter images of it. And you can see this is an area about the size of the orbit of Neptune. So just to get a sense of scale for just exactly how big these debris systems can be, and you can see where our solar system would fit in comparison. So in any event, this is more or less how you start to get asteroids. Here's another fabulous image that I think really illustrates the point. This is a little tiny piece of a comet. And zooming in here, this is an image from Hope Ishii at the University of Hawaii. And if you zoom in, you can really start to see these are the aggregates of all of these little particles of dust that have accumulated over time. And eventually these things grow, and this is what becomes the asteroids and the comets that we have left over today from the formation event. Okay, so now talking specifically about the near-Earth objects, why do I keep saying object instead of just asteroid? Well, in this case, I mean two classes of objects. I'm referring to both asteroids and comets. When we talk about asteroids, people typically think of rocky objects, things that are primarily composed of rocky and refractory materials. On the other hand, we have comets, which contain a lot more ices mixed together and all held together in a rocky matrix. I like to think of them now as kind of opposite sides of a spectrum. Today we know that asteroids span the gamut of everything from really nearly solid pieces of nickel and iron to things that are very weak assemblages of rocky materials mixed together with ices that are very much like comets, that can sometimes, in some cases, we think, be comets that have just gotten too close to their central star and have lost a lot of their icy material. On the other hand, you have the comets, which are mostly mixtures of ices and rocks held weakly together. So these things span the gamut. Sometimes we see objects that look like, from their orbits, they have perfectly normal main belt asteroids, nearly circular orbits, and yet sometimes they sprout tails, just like a comet does. And on the flip side, like I mentioned, sometimes we see asteroids where it looks like this thing used to be a comet, and has just made one too many passes by the sun. But in general, that's why we say near-Earth objects, because we refer to both classes of types of things, asteroids and comets. Now, the classification of something as a near-Earth object has to do with its perihelion, the closest approach point to the sun in its orbit. To be classified as a near-Earth object, it has to get within 1.3 astronomical units of the sun. That means 1.3 times the distance between the Earth and the sun. And that's just how we classify these objects. Okay, so from an origins perspective, why would we care about these? Well, of course, they can impact the Earth, and that can have major consequences for life, both good and bad. These are sources of volatile rich material that can be delivered to the Earth. There's been a lot of discussion about exactly how much influence that had on the accumulation of water on the early Earth. And of course, obviously, these objects can cause tremendous disruptions to our biosphere, and we'll see evidence of that here coming up. Okay, so I have posed here 4 questions about small bodies, and we'll try and step through each one of these here. To just, from my perspective, these are questions that I think are interesting. For one thing, we would like to know when impacts occur, and in fact, specifically, we'd like to know not just on a geological timescale, but we'd really like to know what happens on what I would call a kind of a human timescale. In other words, the next century or so. We'd like to know what will happen in our next century. Will there be a major impact? And if so, how bad might it be? So we could answer both of these questions by finding the objects, tracking their orbits, and then also be able to say something about the severity of impact, which basically boils down to constraining the kinetic energy. And that in turn really just boils down to the impact energy, which is the mass times the velocity squared. We get the velocity once we know the orbit of the object, so now the problem is how do we get a good estimate of its mass? Well, that boils down to constraining density, but the diameter is really the key parameter because the mass scales as the diameter cubed. So in other words, small errors in measuring the size of the object can have a really big effect on the potential impact energy. So we'd really like to know the size. Then we have a whole host of other parameters we'd like to understand, such as the density, the porosity, object shape, spin state, and multiplicity, if it has any binary or other moons that are orbiting it. So these are some of the questions. We'd like to know when and how bad. And then from an origins perspective, we'd also like to understand just, how much of this primitive, unprocessed or very minimally processed material is there among the small bodies in the solar system. And we'd also like to understand how this material can get transported through the solar system and eventually arrive at the Earth. So we'll look at that as well. So from the question of when, now going back, so we have a really unusual event in terms of asteroid science that occurred in 2013. And this was really quite an amazing event because on this very day, there was predicted to be a close approach of an object, but its orbit was very, very well known, and it was not supposed to impact the Earth at all. So when this occurred, it was a huge surprise. And I remember hearing about this on the radio and thinking that this doesn't make any sense. We knew this object was going to pass, and it had really, really no chance of an impact. As it turned out, this was a huge cosmic coincidence. There really was a second asteroid, completely out of the blue. It came from the direction on the sky nearly close to the sun, and it exploded over the surface of the Earth in Russia. So here are the contrails. One of the reasons this is an important event is because it is so well studied with all the dash cams and security cameras and cell phones that people had. We have a really good idea of what its orbital trajectory was. That's how we know it was a completely separate object from the original one that I mentioned. And we also were able to recover fragments and pieces of it. So it broke a lot of windows. This object exploded high up in the Earth's atmosphere. It was not large enough to make it intact all the way to the ground. So that's really, really good. But it was able to break a lot of windows, and it did send about 1,600 people or so to the hospital, mostly from injuries from broken glass. People saw the explosion in the sky, and they went to the windows to take pictures of it, and then the shockwave hit. So, but this does sort of beg the question as to exactly when the next impact might occur on timescales that we are caring about, or that we care about as people, on the scale of the next century or so. Okay, so these guys they do make it out, but yeah, it was quite a surprise for everybody. So again, how often does this happen, and what are we doing about it, if anything? What should we be doing about it? So this now is one of the very best studied objects right here. And this is, of course, the famous Chixolube impactor that hit off the Gulf of Mexico. So the object that exploded over Russia was very, very tiny. We think it was somewhere in the neighborhood of only 17 to 20 meters across. But this object was much larger. This was an object that was somewhere between 5 to 10 kilometers across. And now the impact doesn't just break windows, of course, it creates global effects. You can see here there's evidence of the ring structure of the crater that was left behind here. This is a radar image from NASA, from the space shuttle. And you can see here just the scale of it. This created about a 200-mile or 200-kilometer wide crater. And the signs of the impact are spread across the globe in the fossil record. It had an enormous effect on the Earth's biosphere. I've got a plot here of the number of genera, so one level up from species, going back over roughly 500 million years. And you can see the diversification of life as time goes on, eventually reaching the impact event here. So it did really have a profound impact on the biosphere, resulting in mass extinctions. Life does eventually recover, but it takes of order of, say 5 to 10 million years or so for it to come back after that. So it really did have a profound effect, and of course was, we believe, responsible for the extinction of the dinosaurs. So the question is, how often does this happen? Well, we know that really large global impacts, like the one that wiped out the dinosaurs, really truly cannot be very frequent events, or we would not be here. Human life probably would not be in its currently state if that was a frequent occurrence. So we think that things like this happen of roughly the scale every 100 million years or so. But smaller impacts can happen much more frequently, because one thing we know about asteroids is that they break into pieces, and we'll talk about that in a little bit, creating a shower of smaller fragments. So there's a lot more small pieces out there than there are of the really big ones. We believe that objects of the size of, let's say, the object that exploded over Russia, which was roughly 20 meters across, might occur every 100 meters or 100 years or so. But again, it's difficult to tell because our statistics are small. So from my perspective, the sensible thing to do, if we really want to answer the question of the next 100 years specifically, is to go out and look. But you can see evidence of craters here all across the Earth. This is a particularly large impactor, similar to Chixolube, not quite as big, but this was an impact that probably occurred, I think this is about 250 million years ago, ranging in size to about 1 kilometer across to another object that exploded over Russia in 1908. Okay, so another event that really caught the world's attention, that these are impacts that can occur not just on geological timescales, but really on human timescales, is the discovery of a comet in 1992 called ShoemakerLevy 9. This was an object that was discovered just prior to its impact with the planet Jupiter. And Jupiter sort of tore the object into pieces as it proceeded toward the impact in 1994. And there was a lot of debate within the community about exactly what would happen to Jupiter when the comet impacted on its surface. And sure enough, there's some really spectacular images that were collected by the Hubble Space Telescope, documenting that indeed, the comet did leave detectable scars on the surface of Jupiter. And in fact, each one of these is sort of roughly the size of the Earth itself. So that certainly got everybody's attention. And at present, NASA has been given some goals by Congress. So the first goal was the so-called space card goal, which was to find and track all of well, not all, but about 90% of the kilometer-sized and larger near-Earth asteroids. Now, I didn't say comets, but near-Earth asteroids. And that took the community about 10 years roughly to complete. And at this point, we now believe, the good news is that we've found more than 90% of all the kilometer and larger near-Earth asteroids. So that's the great news. Now Congress has given NASA another objective, which is to find 90% of all objects, of all near-Earth objects, larger than 140 meters across. Now that seems a bit specific. Why 140 meters? Why not 100? Why not 200? Well, roughly this is the size where this is an object now that's capable of causing what we might call severe regional damage. So in other words, damage on a pretty wide scale that would certainly cause global effects in its consequences. So at this point, that's what we're working on now as a community, and we're making some progress, but we have a lot more work to do there. This is the current suite of the observational program carried out by NASA. There are a few other telescopes that I have not shown here, but these are some of the workhorses. So we've got the Catalina Sky Survey here in Arizona, Pan-STARRS, 2 telescopes in Hawaii. A new telescope that's being deployed in the southern hemisphere, and I'll talk about NEOWISE because that's the project I work on, in space using infrared wavelengths of light instead of visible light, like the other telescopes. So this is the progress that we've made to date on near-Earth asteroid discoveries. And if you separate these out by size, the kilometer-class near-Earth asteroids, you can see here, this curve is relatively flat, which we believe at this point means that we really have run out of most of the objects to discover, and that we really have found the majority of these objects in this very large size category of asteroids. But for the smaller objects, the curves just keep going up and up and up, meaning we haven't come close to exhausting the population yet. And if we break them down today, with the telescopes that we currently have, right now, most of the things we're discovering are on the smaller size end of the scale. And that is because we are limited in what we can see. We kind of just can't see that far away from the Earth. So we kind of have to wait for things to come to us. And as I mentioned, there are a lot more small pieces than there are really big ones. So we're having a harder time achieving those really high levels of completeness on the larger objects. And to do that, we need more capability that can see further away. So at present, when we look at the goal that NASA has been given by Congress, we think that we've found somewhere in the neighborhood of 30 to 40% of the objects large enough to cause that severe regional damage and up. So we still have a lot more work to do. And we are looking at some ways to expand capability. As mentioned in the introduction, I am working on a new project with the team to build a more comprehensive survey telescope that will be capable of seeing things further away, called the NearEarth Objects Surveyor. And its objectives are simply to go out and fill out our knowledge of that population of objects that are large enough to cause severe regional damage, and then hopefully help to provide some guidance on things like the sizes of the objects. We'd like to really be able to find these objects and do a sort of a basic physical characterization of them, and do it as quickly as possible. Okay, so that's the Near-Earth Object Surveyor mission, which we expect to discover hundreds of thousands of new near-Earth objects and millions of more distant objects in the solar system. It will do so by operating at the Earth-Sun L1 Lagrange point. So the idea is to be just outside the orbit of the moon, where we can sit and survey these very wide swaths of sky. And in particular, we really want to look for asteroids that have very similar, very Earth-like orbits similar to the Earth, because that allows them to have more chances of making a close approach. I'm going to go through this a little quickly here, but basically the idea is we have ground-based telescopes like the Vera C. Rubin Observatory that's coming online that will survey large swaths of the night sky, and we'll be looking over here at these cones that sort of look at the regions of the Earth that are closer to the, or rather regions of space that are closer to the sun on the sky. So it'll provide some complementary capability to look out for all kinds of different asteroids, including ones that have very circular Earth-like orbits, as well as ones that have more elliptical orbits. Okay, so in any event, if we get going on the sky as we expect, we hopefully will reach, with all of the surveys combined together, in not too very long, we will be able to get pretty close to that 90% goal given to NASA by Congress. So if we do that, hopefully we'll have a quite comprehensive survey of the near-Earth objects in our solar system and in the not too distant future. So how do we do this? Well, we've got to look for things that move. And of course, there's a lot of confusing sources out there in the sky, including stars, galaxies, and even other more distant asteroids that really pose no hazard whatsoever. If we take this example image from the existing space telescope that we have, which is NEOWISE, we can take a look at what we expect the field of view to be from the Earth Object Surveyor mission. So it'll be a pretty large swath of sky we'll see at any one time. There's all kinds of interesting things in the sky that we have to watch out for, though, that are potential sources of confusion, like this lovely planetary nebula here, a bunch of galaxies, clusters of galaxies, interstellar dust, other artifacts from the telescope itself. So how do we find the asteroids in all of this? Well, in this particular set of data from WISE, we can start to suppress the background sources. So basically map the things that don't move and mask them out or subtract them out. And now we can just barely start to see the moving objects popping out, and there they are. These are mostly main belt asteroids, however. These are asteroids that are far away and never make really close approaches to the Earth. So we care about them from a scientific standpoint, but from a hazard perspective, we want to get rid of them. We want to eliminate them. There are other artifacts we have to watch out for. We can start to identify these ones as known objects. But here is a particular one, and you can see its motion is quite different on the sky from the more distant main belt asteroids. this object is what we call a potentially hazardous asteroid. It has one, that means its orbit carries it quite close to the Earth's orbit. Doesn't mean that there'll ever be a collision with this object or anything like that, but it does mean this is an object that we pay much more careful attention to, and these are the real targets of our search from the hazard perspective. Okay, so if we are successful in our efforts to get the survey telescope built, basically, once it launches, it will very quickly go out and survey the asteroid belt and the near-Earth object population. It should accumulate a lot of things very quickly and hopefully getting us very close to that 90% goal given by Congress to NASA. Okay, so that's a little bit about the when question. If we can find the objects, get good orbits for them, we can figure out when they might make close approaches. But now the question of how bad an impact can be answered. And to do that, we need to make some basic measurements, like I said, of the object's physical properties. Most important are the diameters as well as the densities. So returning back to that object that exploded over Russia, this is the single largest crater, if you will, that the object made. And it's basically a 6-meter wide hole in an icy lake. This is the largest piece that was recovered right here. On the flip side, like I said, this was an object that was relatively small, about 20 meters across. It broke a lot of windows, but there was no big crater. On the other hand, if the object is just slightly larger at 50 meters across, now instead of a small hole in the ice, you get a kilometer-wide crater on the ground. I actually have a couple of pieces of meteorites here, which I'll hold up. I hope everybody can see these. But this little piece right here, this is a piece of Chelyabinsk. So the object right here, this is one of the fragments. And I also have a little fragment of the object that made the crater on the right. So this one, it's a bigger piece, but I don't know if you can see it's really heavy. And that's because its predominant composition is iron. So you can see even very small changes in the size of the object when combined with its density can make a very big difference in the outcome. So that's why we'd like to measure the sizes, and we'd like to have some way to constrain important properties like density as well. Okay, so in measuring diameters, we have several different tools in our arsenal that we can use. One of the ones that we've been working with in my group is to use infrared measurements. So in other words, if we look at the spectral energy distribution of typical asteroids, so you can see that it consists of kind of two curves here. In the visible portion of the spectrum, you can see reflected sunlight bouncing off the surfaces of the object. And then it's re-radiated as heat. As the sun warms up the asteroid, it gets re-radiated in these longer thermal infrared wavelengths. And the 4 colorful bands here represent the 4 filters that we use on the WISE mission. I've got 2 different albedos here. Albedo is how much light is reflected off the surface of the object. This right here is a more typical stony object at 17% reflectivity here, and I'm holding up the little piece of Chelyabinsk. In other words, these objects are kind of lighter in color. On the flip side, we have objects that are extremely dark and reflect very little sunlight in optical wavelengths. And here is a piece of a very primitive type of meteorite called Allende. You can see it's quite dark in color. So they range in reflectivities quite dramatically, and this can have a big influence on how detectable the objects are. Also, how well we can measure the size. So in a nutshell, if we can collect thermal infrared measurements that sample how much heat the object is emitting, we can, if we know the distance to the object, we can turn that into a pretty good measurement of the object's diameter. Now, I kept mentioning the WISE mission. This is an Earth-orbiting telescope that was launched in late 2009, and it was really designed to do something else. The principal investigator is Ned Wright of UCLA, and it completed its prime mission, making a map of the entire sky at these 4 infrared wavelengths that you see here, ranging from 3 to 22 microns. It finished its mission in 2010, but it turned out that even though its primary science objective was not to look at asteroids, it was actually quite successful at doing so. And we've been able to measure about 190-some small bodies, including a couple thousand near-Earth objects with it. It completed its prime mission in 2010, and we thought that was the end of it, but NASA asked us to switch it back on using its 2 remaining channels after the 2 longest wavelength channels are no longer operational. And so now today we are surveying asteroids and comets using these 2 remaining channels here at 3 and 5 microns. So to date, we're continuing to measure asteroids, and even though predominantly we're not discovering that many objects anymore, what we're really good at doing is measuring their sizes. And that's what the focus of the investigation has been. When we look at the sky, another reason for using infrared light to look for these objects is that the asteroids kind of stick out brightly compared to the stars. And that gives us an advantage in finding objects, particularly those that are made of less reflective material, and that's helpful. So even though at visible wavelengths of light, an object might look like it is different brightnesses, it could just be that we are sampling objects with different reflectivities and different sizes. In other words, it lets us, if we use infrared light, we can tell the difference between an object that is small but highly reflective versus one that's much larger but has a very low reflectivity surface, sort of like a piece of charcoal. Okay, so I'm going to kind of whip through these. I'm not going to walk through the equations, but the point of this is to just simply say, if we have a good measurement of an object's brightness at infrared wavelengths, and we know the distance to the object, then we can actually calculate its size. And the way we do that is we have to make a measurement of its temperature and convert that measured infrared flux, or the heat from the object, back into a diameter. And that is what we do with what we call thermal modeling. So basically, in this case, we would make an assumption of the way the temperature is distributed around the asteroid, and then from there we can back calculate the size. So if we do that, we can now get a pretty good measurement of how big the object is, which goes back to the question of how severe an impact is likely to be. We can also, in some cases, calculate other parameters like the albedo or the reflectivity, and that helps us learn something about its probable composition. Okay, so if we're successful with getting good thermal infrared measurements, we can usually constrain the diameters to between sort of 10 to 20% on average. Occasionally, you can do a little better if you have a lot of observations, but I would say with good sampling, you can typically know the diameters quite well. On the other hand, if all you have is a visible light measurement, it's harder to do this in general, simply because you have a pretty wide range of potential reflectivities of the surface that we have to account for. Okay, and in addition, the infrared light is sensitive to both the highly reflective objects as well as the really dark ones, and that helps us get a very good census of the population to understand exactly how many objects are out there. So when we do this with NEOWISE, we basically can make a plot of the sizes of the objects compared to their reflectivity. And one of the things we found is that when we make this sample of near-Earth asteroids that are chosen purely based on how much heat they emit, their 12-micron flux, so how much light are they emitting in the thermal infrared, what we see is that there really isn't a huge change in the distribution of the ratio of dark to bright objects over a fairly broad range of sizes. In other words, we believe that there are these smaller, low albedo objects out there in the population, but you have to look in such a way that you can actually see them. So other things that we have noticed in the course of doing this survey is that objects that are discovered using the infrared telescope tend to be on the larger size, and they are predominantly low albedo. So we are picking up this low albedo portion of the population that we believe is out there, but can be difficult for visible light telescopes to see simply because they're optically dark, and that means they're faint. But they are there nonetheless. So what is the nature of this, and how much of this low albedo material? As I've said before, this is some of the least processed material in the solar system. It comes from the farther, more distant reaches of the presolar nebula. So it's evolved in a region where it's very cold, and it hasn't experienced a lot of thermal processing over the course of the solar system's evolution. We believe from our survey with NEOWISE that roughly 30% of the objects that make it into near-Earth object space are made of this low albedo material, and of course some of that is getting delivered to Earth. So we also now have samples back from one of from a very well-studied primitive asteroid called Ryugu that was the subject of the Hayabusa 2 mission. So this was a spacecraft that actually was launched by JAXA that went to this asteroid, collected a sample of it, and was brought it back to the Earth. And you can see it here. It's extremely dark material, and it looks like charcoal. So I've got, like I said, I've got a sample of this object here. This is another primitive meteorite that's been found on the Earth. But yeah, you can see that this is material that is extremely dark, and so we believe that this is material that is often altered by the presence of water that has been mixed throughout the material, and over time has produced a lot of complex chemicals that have arisen. So this in turn could be very important for how life evolves on not just our planet, but potentially others in other solar systems as well. So where is this material presently distributed throughout our solar system? Well, we know in a broad sense how this works, but now let's take a look at exactly how the details seem to have evolved. So in asteroids, we have what we call families of objects. You have objects that basically undergo catastrophic disruptions. They collide with other asteroids and create a shower of fragments. And that's how we get groupings of asteroids that share similar orbits and similar physical properties. We believe that they originated from a common parent body. By looking at the characteristics of these families, we can sort of map out the distribution of this carbonaceous material throughout the solar system and try to understand a little better how it is distributed. So when we do this, this is my colleague Joe Massaro who made these plots, we can basically look at the orbital properties of asteroids. So now if we look throughout the main asteroid belt, so this is the region between Mars and Jupiter here, and if we plot this semi-major axis of the orbit, so in other words, how far away do the objects get from the sun, compared to their inclination, so this is basically how tilted the orbit is. When we look at this, we can see some really distinctive patterns when we plot them by their geometric albedo, so their reflectivities. You can now see that there are these clusterings here. So certain objects that are sharing very similar orbital elements, they're grouped together, and they have similar reflectivities of their surfaces. So they seem to be made of similar material, potentially. We call these asteroid families, and we believe that these are the products of catastrophic disruptions. So something collides with another asteroid, and it creates this shower of fragments, and they stick together throughout the main belt. When we subtract these asteroid families from the background population of all the asteroids that we know about, in other words, these are the ones that we believe are dynamically connected together, that they did share a common parent a long time ago. When we take these out, we can now look at the background distribution of asteroids. You can see that the subtraction of the asteroid families is not completely perfect, but there are some trends that emerge. The material appears to get darker in its reflectivity as you go further out into the solar system. So as we go from the inner edge of the asteroid belt all the way out to its outer extent, you can see that the material is becoming, in general, lower in albedo. And we believe that means that this is where some of the most primitive material lies, in the outer parts of the asteroid belt. But occasionally, some of it does make its way to the Earth. So one of the other things that we've looked at is when we take the collection now, instead of main belt asteroids, when we go back to the near-Earth object population, because this is the population that is actually capable of reaching the Earth itself in the present day, we can look at the different categories of near-Earth asteroids. And so again, plotting semi-major axis versus orbital inclination, so again, the tilting of the orbit, or its eccentricity, which is essentially how elliptical the orbit is. There are some trends when we look at the albedos. We can see that near-Earth asteroids that extend in their orbits, that have orbits that carry them further out into the asteroid belt, they tend on average to have lower reflectivities than the ones that have more circular and more Earth-like orbits. So that's another general trend that we've found using the NeoWise data. But we'd really like to, like I said, we'd really like to understand exactly the nature of this material and how it gets transported to the Earth. From an origins perspective, I think. So again, these objects are things that have been altered by the presence of water throughout their matrices. And at present, they do contain materials such as phyllosilicates, in other words, clays, as well as amino acids. So really exciting from an origins of life perspective to see that these objects have such complex chemistry. Okay, so now let's look at a little bit of the delivery mechanisms, just so you have an understanding of how this material does arrive at the Earth, or how we think it arrives at the Earth in the present epoch. Now, I had mentioned before that when something is in the main asteroid belt, it stays there on average for billions of years. Most of the time, that's what happens. However, there are a couple of exceptions. It is possible to move through the main asteroid belt and make it into near-Earth object space via a couple of different important mechanisms. One is called Yarkovsky drift, and I'll explain that in a minute, and the other is through resonances with planets. So kind of a broad way to think about it is the influence of sunlight and the influence of gravity. So let's look at the first one here, and these slides are from a colleague of mine who I thought did a really nice job of illustrating this. You can imagine that there's something that happens to asteroids when they get heated up by the sun. The conservation of energy requires that the energy has to go somewhere. Energy is absorbed by an asteroid, and that can cause it to basically have essentially a recoil action, if you will, as the sunlight is absorbed and then re-radiated as the asteroid rotates. And that actually kind of causes a little kick to its orbit, and it can actually push the object into a spiral inward or outward. In other words, it changes the orbit. Even just that faint effect of sunlight being absorbed by the object and re-radiated at a certain time of its local day is enough to change its orbit. Now, it takes a very long time for this effect to happen. This is not fast. This acts on very slow timescales, but it's enough to cause gradual drifting of the object's orbits. And when that happens, now gravitational resonances can take over here. And I've got a couple of examples of what I mean when I say resonances. This is an example of what we would call a 2-to-1 resonance. So imagine if you're swinging on a swing set and you kick your legs, and if you kick your legs at just the right point in your swing, you'll go higher and higher and higher. Well, the same thing happens with planets and asteroids. Once objects' orbits get locked into certain classes of resonances, if you put an asteroid near these planets, now what will happen is its eccentricity, the squashiness of the orbit, if you will, can get pumped up and can get increased dramatically. And that can really change the orbit fast. So basically, you've got a couple of different classes of resonances that can happen with the planets in our solar system. And when asteroids get into these resonant regions, they can basically get acted upon just like a slingshot. And here's another example of a different type of resonance. In this case, the two planets start out of resonance, but here now you can see the effects of them being in resonance. You can see their aphelia, they reach aphelia and perihelia at the same time. And that can, again, cause this really dramatic effect on an asteroid's orbit if it just gets into the wrong place in between these planets here. So like a slingshot, all of a sudden now the orbit can change really quickly. So here's an example of this. If we look at a certain region of the main asteroid belt in semi-major axis, so distance from the sun roughly, it was one way to think of it, versus the object's eccentricity, so how round is the orbit. If we start off with a set of test asteroids here and we let them evolve, you can see when they cross into these gravitational resonances, which are marked out here in green, now you can see the eccentricities change very quickly, and the asteroids can dramatically change their orbits. And what this means for the near-Earth asteroids is that you can start off here and in a certain region of space, certain orbit, and now you can get evolved very quickly on timescales of just a few million years into planet-crossing orbits. And now you can have impacts. So in conclusion, I would say small bodies influence life on Earth, and that's why they're interesting from both a hazard perspective as well as an origins perspective. So with that, I'll stop here, and thanks very much.
Wow, thank you very much. That was an amazing talk. Questions from the room? All right, I'll go over here first. Thank you so much for your talk. I was really curious about when you were specifying like the NASA wanting 90% of near-Earth objects being detected. How do you establish those thresholds when you don't know what's left out there?
That's a really, really, really important question. And there are a couple of ways that we answer that. One is what we call the redetection method. So in other words, each time we discover an asteroid, we give it a name and we can keep track of it. So one way to test this is to see how often we come up with objects that we've seen before. In other words, if we keep seeing objects and now after a certain period of time, we just keep finding ones that we've seen over and over and over again, and we stop finding new ones, that's a clue that maybe we're starting to run out of objects. But it could also mean that our survey is simply not very sensitive. That's another possibility. So to rule that out, we have a second technique that we use where you essentially make a synthetic population of asteroids. So you assign them synthetic orbits and sizes and so forth, and you essentially build a model of your survey. You basically sort of play a movie, if you will, of using the synthetic population of asteroids, and you play it through your survey, and you see what the synthetic survey actually comes out with, and then you compare it to what you actually saw. And you tune your input population until these two things match, essentially. And then that tells you, okay, this is how many objects are actually out there in the population, and then this is the fraction that we believe that we found. So in other words, there's a couple of ways that we can use to get at what we think is really there. And they work, like I said, we're pretty sure at this point we found the majority of the really big near-Earth asteroids, and we think we're somewhere in the neighborhood of 30 to 40% for the 140 meter class objects. Does that make sense?
Yes, it made sense. Thank you.
Okay, thanks.
Hi, Dr. Mainzer. Thank you so much for the talk. It was really interesting. I had a quick question on basically the Chelyabinsk impact. You had said something to the effect of it. We thought that we had tracked something that wouldn't come anywhere close, and then it turned out there was something that we didn't realize that was sort of out of the blue. I think you said it was in the direction of the sun or something like that. So
That's
I guess
right.
my question is, to what extent do we have an estimate of similar situations happening where we might get misled about potential impacts or things like that?
Yeah, this is a key question. For an object of the size of the Chelyabinsk impactor, at about 17 to 20 meters across, we only know a few percent of those objects at present. So they're just really hard to find because they are faint. We have to wait until they get really close, until we can spot them at all. And in the case of this particular object, the direction that it came from as it made that final plunge really was nearly in the direction of the sun. And that's a direction our telescopes just can't look because the sun is so bright. So yes, it can definitely happen. That's why we're trying to expand our search capability so that we have more telescopes looking in more different directions with greater sensitivity. That said, I mean, we still can't look right in those regions very close to the sun. That's really hard to do. So with the Surveyor, we're going to try to survey pretty close. We'll get to within about 45 degrees of the sun on the sky. But it's still, we'll expand our capability, but there are definitely still going to be objects where we're not going to be able to see.
Dr. Mainzer, thank you for your talk so far, and wanted to ask if you could address the question around earthbound observations of NEOs with respect to mega constellations like Starlink or OneWeb and what the impact of those would be. Obviously, it'd be great to be more space-based, but that's really expensive. But if you could address Earth-based observations and the impact on these mega constellations.
Absolutely, and that's a very important point. And I have some colleagues who are doing some really wonderful work on this to try to understand the impacts and quantify them better. I mean, certainly from an observer's perspective, more things that are potential sources of confusion are not good. It doesn't make the problem easier. Let's put it that way. It can only make it harder. So it's definitely not helping. And the more objects there are, the more confusion that they will cause. So it's not a good trend. There is a paper that just came out by some colleagues working with the Zwicky Transient Facility who have tried to start quantifying, what they're seeing today. And yeah, I mean, it is really a source of concern, I think, because it just certainly doesn't make the problem any easier. Right now, the paper from the ZTF team indicates that they can do a fairly effective job of masking them out if they know where they are. But as the constellations grow, it's just going to get to be a harder problem. Absolutely. So I would say not good is the short answer.
We've got a couple of questions coming in from online. One question is, in light of the influence of small bodies and delivery of the objects and the materials in them to Earth and places like that, what are your views on the theory of panspermia?
Oh boy, well, I'm certainly no expert on the origins of life, but I will say it's just really fascinating to think about. There's a whole set of really, really interesting experiments that just show how complex chemistry grows on the surfaces of dust grains. And Dr. Ishii showed that. I showed that slide from her imaging of a dust particle. Well, basically, we think that these are wonderful surfaces for chemicals to meet up and become more complex chemistry, essentially. So the surfaces of dust grains are great nucleation sites for chemistry to happen, especially as they're irradiated by their host stars. So, could life have evolved elsewhere? I mean, there's so many planets now that we know about. It seems to me that it would be very probable. Exactly the mechanisms, though, that's a mystery, and I sure hope people will work on that because I think it's a really exciting problem.
Awesome. And another question from YouTube. Dr. Mainzer, you mentioned that these small near-Earth asteroids contain amino acids. As a microbiology PhD student, my question is, how are the building blocks of life incorporated into asteroids? So, very similar question.
Right. Okay. So we are definitely testing the boundaries of my knowledge here, but I'll tell you what I know, which is basically that that we know that we can study these objects as they come to Earth in the form of meteorites. So like I said here, this particular object is a well-known primitive asteroid or meteorite called Allende, and you can see there's a lot of small kind of whitish markers inside it there. I don't know if there are features in there. Those are called chondrules, and these are things that are really left over from the very beginning of the solar system's formation. So they're quite old. But in an object like this, you can still find evidence of this complex chemistry. So perhaps it means that this process got started quite early in our solar system's formation, within the first billion years or so. Again, this is really at the boundary of what I know, but I would say that it's very probable that this is a process that happens in other solar systems, I would think. And exactly to what degree it influenced the development of chemistry here on Earth, I don't know, but it's definitely a fascinating question.
Hi, so my name is Micah Scheibel. I'm a research scientist here at Georgia Tech, and I wanted to just poke a little bit at sort of, you did this movie advisory role, and I was wondering how your work sort of fits into the small comets world. How likely is it that we're going to have an Earth-crossing small comet that we just don't know about?
Right. Yeah, that's a really interesting point. So the good news is we know that, like I said, these really large, globally catastrophic events, they have to be infrequent, or we wouldn't be here, I would say. But there are a lot of smaller pieces out there, and we do our best to keep track of them. But occasionally some of them, make it into the inner solar system. I think, the chance that the saving grace with the comets is that in terms of the ones that make it into the inner part of the solar system, they are far fewer in number than the near-Earth asteroids. So in other words, even though comets can on average be a lot larger than a typical near-Earth asteroid that we're keeping track of, they tend to be, they're bigger, they move really fast with respect to the Earth, so they can pack a huge punch. But the saving grace is there are fewer of them that really make it into this part of space right near the Earth. So that's the saving grace. But that said, we still have to keep an eye out for them. They are out there. Yeah,
that's great. So do you use the same surveys to look for those, or is it a different survey?
Yeah, we're using the same surveys. And you raise an interesting point. Should we be doing the survey in the same way? In other words, do you want to look on the same part of the sky with the same number of revisits and so forth? Should the survey cadence change as a result of the orbital elements of the thing we're searching for? So far, the good news is that the near-Earth asteroids tend to have a pretty broad distribution on the sky in terms of their orbital inclinations, in other words, the tilts of their orbits. So that's good from the perspective of looking for comets, which the long period comets really are isotropically distributed. They're all over the place. So far, that means our basic search strategies seem to be effective at both populations. That said, as we get further along in the survey, it's possible we could refine things to spend more time looking at high inclinations, possibly. Kind of depends on what we find. Does that sort of answer the question there?
There we go. I had to turn the microphone on for a second. There you go. All right. I'm more of a biologist, but I have a question more about how these things might change over the course of history. When you were talking about the way when you create a family and the family then expands through phase space and starts becoming crossing, seems like that could lead to sort of a cluster of events in time. And I'm wondering if you think if there's any indication if sort of there's just sort of a constant background of these things, or if clustered events like that might occur in time, and how much if those might be a reasonable part of what happens, or if just generic background might be a bigger deal.
That's also really interesting. And there's this period called the late heavy bombardment that we think happened fairly early on in the solar system's formation, so kind of in the first billion years or so, where there was a reshuffling that happened, which sent a volley of impactors into near-Earth space. And so the Earth was, we think, kind of really pelted with objects back in that period, and then it sort of tapered off after that. But you're right, you can have these family-forming events, and if something happens close to a resonance, it can really affect the local influence or the local flux of objects onto the Earth. So one of the things I'm interested in looking at, hopefully eventually, is to try to probe that in greater detail, because it doesn't take a huge object to collide to produce a lot of fragments. So we know sort of the broad brush picture of how it happened with the late heavy bombardment, but the exact specifics of what happened since then, I think we would like to have more data to be able to probe that in greater detail, which hopefully we're going to have soon.
Great. Thank you so much, Amy, for your wonderful talk. We really all enjoyed it. There are a few more questions that populated in the chat that we could have you take a look at later if you would like. But we will be moving on to our final session of speakers here.
Great.
Yes,
Thank you so much. Thank you.